Morning, everybody. All right. We need to talk about angular momentum. So we left off last time with the cross product, this mathematical definition of how to multiply vectors together. And the whole reason that we had to learn about the cross product is because angular momentum and torque turn out to be a cross product. With both torque and angular momentum, we're getting another vector out of putting two vectors together. So let's do some definitions and write down some things, and then we'll see where we get with applying everything that we've learned. So what was standard momentum like from chapter 9? Anybody remember? It was too long ago. No. What is momentum? I'll help you out. It's early in the morning, right? Okay. Mass times velocity. Okay. And it's a vector, right? It follows the direction of the velocity. I heard some of you going directly to impulse, which is, related idea and an important one. So, wouldn't it be nice if our angular momentum were just, instead of regular mass, rotational mass? And instead of linear v, it would just be angular omega. That would be nice, wouldn't it? Well, that's what it is. Yay, right? Hey, great. Only this is where it kind of goes wrong. The symbol for it is capital L. Everybody knows that momentum is spelled with a silent capital L, right? Apparently. It's just so weird to me. So that's one way to think about it. And it does flow and follow from the definition that we had for momentum from before. And you're like, but Mr. Balogh, there's no cross product there. I know. That's because angular momentum turns out to be the cross product between a distance from an axis of rotation, this radius again, this r vector, crossed into a momentum vector. This is strictly, right, angular momentum. So anything that is moving, because momentum is just mv, anything that's moving, as long as it is moving near an axis, it doesn't have to be moving in a circle, as long as it's moving near some point that we're defining as an axis of rotation, can have angular momentum. There's only one situation where something can't have angular momentum, and that would be if the angle between a distance from an axis and the momentum were 0 or 180 degrees. Because the cross product between any two vectors that are parallel is always going to be 0 or anti-parallel. So that's kind of handy. But in general, right, for circular motion, let's just take a look at a circle. Nah, it didn't work. Supposed to make me look good, softer. There we go. Okay, so if we have an object that's moving around, right, in a circular path, we can draw this r vector, right, from the center of the path to where it is. It's going to have this velocity right here. And if it's a circular path, that means that those two things are always perpendicular to each other. And perpendicular is kind of nice, makes things sort of easy to do. So assuming a circular motion, right, then this angular momentum vector's magnitude can be found by doing one of our cross product things right here. Okay, instead of having to go into this huge matrix and figure out everything in 3 dimensions, I can use this idea that I can find the magnitude of my angular momentum, right? It's first vector, second vector, sine theta. So that's what I'm going to do right here, right? The magnitude of my angular momentum is going to be first vector. times second vector, their magnitudes, right? And then the sine of the angle between them. Well, what's the angle between these two vectors? 90 degrees, like I just said. What's the sine of 90? It's 1, isn't it? Okay. So theta is 90 degrees for a pure circle. I get an angular momentum, right, of RMV, which is, again, great as long as you understand that that one is only for a circle, right? And if we use our Google Translate, where we can go from V's to omegas, well, what does this turn into? We get an R times an M times an R omega. Yeah, we get the, I'm going to write it this way. We get the MR squareds omega. And what's MR squared? Anybody remember? It's moment of inertia. It's like sort of the base definition of moment of inertia for a particle, right? And so again, here we are at moment of inertia times omega. So all three things that you see in boxes on the screen are the same thing, as long as we are talking about circular motion. The one over here on the left, this one is in general for any motion, doesn't have to be a circle. But the two here on the right, and I'll put green boxes around them just to indicate, right, that the ones in green only apply to circles, not ellipses, not straight lines, and that kind of stuff, right? Just gotta have to know where to apply them. Okay, so we got the magnitude of the angular momentum, but it is a vector. And so the question now becomes, okay, well, how do we sort out the direction of this angular momentum? And the answer becomes, well, which hand are you going to choose? The right hand, okay? So we're going to do a right hand rule. All right, so it's R cross P, and that right hand rule is a handshake because we're doing a cross product, and you always shake your hand in the direction of the first vector, so along R in this case, and then you rotate your wrist around so that you can bend your fingers in the direction of V, and which way does your thumb end up pointing? Into the screen. So the direction of angular momentum here would be into the screen. Last chapter, we talked about a different right-hand rule, the hitchhiker, right? Where we wrapped our fingers around in the direction of rotation. It turns out this works for this example as well. Because if we follow omega, if we wrap our hands around in omega, which way is our thumb pointing? Also into the screen, which is no surprise. R cross P and I omega are nearly directly related to each other. Only difference is R cross P works everywhere. Sometimes you do have to go for it if you don't have circular motion, but I omega works for circles. So it should be no surprise that our right-hand rule that we had for circular motion in chapter 10 would work also. All right, so now when we studied regular momentum before, I did sort of drop on you that there was a relationship the way that Newton sort of originally thought of his second law, was that instead of m times a, it was a change in momentum in time that forces were working against. If you're gonna change the momentum of an object, you have to apply a push or a pull. Okay. Well, very similar in angular momentum. If we change the angular momentum of an object, instead of a torque, instead of a force, what are we going to have? I blew it. A torque. Right? So angular version that relates changes in angular momentum to torques. Okay, let's apply some of this knowledge that we've got here about angular momentum. I know I haven't really showed you what angular momentum is. We're going to do some concept stuff a little bit later, but let's just jump in, get some application because it isn't that difficult. Again, we're going to the merry-go-round. And when I say it isn't that difficult, it's not like calculating the numbers is easy, okay? It's putting it all together at the end and getting your directions correct can be a little bit difficult. But let's just, separating out, we'll do the calculation, see what's going to happen, right? Okay? Okay, so we've got our merry-go-round. We've got some object, a lunch pail or something, right? Maybe sitting right here on the edge of our merry-go-round, right? As the merry-go-round goes around in a circle, okay? So if I'm going to draw a picture, I'm going to try to visualize what's going on here. I'm going to draw a top-down view of my merry-go-round. And here's my object sitting on the edge of it, okay? And I've got some distance that they tell me. This is 2 meters. And the object is 4 kilograms, right? And we want to find the angular momentum. Let's see, what do we know? What the 2 centimeters, that's my radius, isn't it? The 2 meters, rather, okay? That's my radius. That's how far away my object is from the center of its rotation. The mass, 4 kilograms, just kind of making a list because I'm not quite sure what my problem-solving method is, but I know it's visualize, strategize, do it, check it, right? They give me a tangential speed, 5 meters per second. So they want me to find angular momentum, right? That's what they're after. If I go back here to my toolbox of sorts, right? Is there any one of these boxes that seems to be speaking the language of this problem? It's the one in the middle, isn't it? Right? We've got R, we've got M, we've got V. Okay? Like I said, the calculations tend to never be all that difficult. Okay? It's getting the application and directions right that can be a problem, which we're going to do in a bit. Okay, so I'm going to go ahead and use R and V. Well, that's 2 times 4 times 5. Is that 40? That's 40, isn't it? Oh man, what are the units? We've got a meter. We have a meter per second times a kilogram. What are the units here? This is just weird. You get quant. Let's go quants. That's a meter. This is a meter per second times a kilogram. That's a meter squared per second kilogram. Dang. Right? That's rough. But that's what it is. Again, it's a Balogh meter. Whatever. Usually this is written kilogram meters squared per second. All right. So weird units, weird idea that you're not quite sure about yet, but at least we can calculate it. Now, let's say for some reason you missed the fact that everything was sitting right here for that problem. And instead you're like, oh, circle, I'm going to go over here, right? Let's talk about that, okay? Spoiler alert, what should the answer be? Exactly the same, okay? So let's see what happens, right? So if we were going to use I omega to calculate this. We need to find 2 things. We need to find I and we need to find omega. Which one do you want to do first? I? All right. So we go for I, right? And we go for the table, okay? And we look at the table and we're looking for an object sitting on the edge of a merry-go-round. What do you think? F? I would agree that F would be the answer if we were talking about the merry-go-round, right? We're just talking about okay? We are just talking about a mass going around in a circle, right? So this is a point particle. It's an object that we're not told anything about the shape, and it's just going around on this merry-go-round, but they're not asking about the angular momentum of the merry-go-round. They're asking about the angular momentum of this object that's moving around in a circle. So is there anything on this table that would suggest an object moving around in a circle? Okay, it's not G, although it's going to be the answer. G and the answer that I'm going for are going to be the same thing, but not for the reasons you think. Yeah, when it's just an object that the shape doesn't matter, and it's moving in a circle, then you default to mr squared. It happens that a thin-walled hollow cylinder is also equal to the total mass radius squared, okay? But for a single object moving around in a circle, you just use mr squared. So if it's a particle or an object, that shape makes no difference, like the mass is not spread out elsewhere in this shape, but the mass is concentrated to one space and it's going around in a circle, then you would use mr squared. The moment of inertia of a kid riding on a horse on a merry-go-round is going to be mr squared, okay? If I'm coming up to this door and I hit the door and I start to rotate with the door as I open it, my moment of inertia is mr squared. The door is going to be like, well, probably D, isn't it? Okay? Because it's got mass spread out in multiple dimensions, okay? But me, there's no Mr. Balogh on the table. Don't any of you look at the solid sphere, okay? But there's no, like, when the shape of the thing doesn't matter, you just default to mr squared. Okay, so that means my moment of inertia is mr squared. And then now we got to tackle omega, right? How do we tackle omega? Google Translate, right? And so that's going to be V over R. Oh, and oh, look, MVR, right? RMV, whatever order you want to put those in. Okay, we'll do RMV to make it look the same, and then I put in all the same numbers, and I still get 40, right? So whichever way you want to approach a problem, right? Whether you use I omega or you use R cross B, if you apply them correctly, you're going to get the same. Now, I did say that this wasn't difficult. Was the math, like, right here difficult? Was, like, this list difficult? No, right? And you're sitting there going, well, this is stupid, Mr. Balogh, because you're lying to us. It's always harder than this. And you're right. It's going to get harder than this because all I've defined for you is angular momentum. Literally, I've just taught you mv, but in a circle. There's a lot more to it than that, isn't there? When we were in chapter 9, we went from mvs to then colliding things into each other. And what does an angular collision look like? The picture you just got in your head is probably wrong. Because it's not two things that are rotating, slamming into each other. That's still a linear collision, okay? So we'll get there. We'll get there. But before we get there, I do want to talk about what happens, how you find the angular momentum of things that are rotating where the shape does matter. So if the shape doesn't matter, it's just mr squared. But if the shape does matter, then you exclusively want to use I omega. R cross P is great for point particles or the shape where it doesn't matter what the shape is. But as soon as you have any kind of mass extended from an axis of rotation, you've got shapes like the ones here on the table, now we just default to I omega, right? And generally these shapes, they're going to be rotating anyway, and it's not the tangential v that matters, it's the rotational speed that matters. So let's do an example of calculating angular momentum of things that are in rotation. And I'm going to use Big Ben as an example, the iconic London landmark that the British people are so thrilled about, I guess, every time it rings. This last May, I got to stand underneath it for the first time, and it was a clock. It's a clock. It was a clock. Impressive architecture, like lots of world history surrounding it. British people have to have something to be happy about in an island that's gray and rainy. No, Britain's a great place, but I didn't really. I listened to it ring. I waited for 5 minutes. I listened to it ring, and then I kept walking. That's basically the Indian food in London was much more exciting than Big Ben. Anyway, so big clock, right? Like in this problem, I thought I fixed this slide, and I always seem to never remember to fix it. The radius or the length, okay, of the hour hand needs to be given. It's 2.7 meters. And the length of the minute hand is 4.5. Okay, so I really got to maybe update this example here. But it's such a good one. This is a clock. We used to tell time with them, right? Used to. Now we just do it with our phones. This is always a fun exercise, okay? Which of the hands in the picture here is the hour hand? Is it the shorter or the longer one? It's the shorter one. Okay, well, obviously I gave a shorter distance, right? Okay, and then the minute hand. So what we're going to do is we're going to find the total angular momentum of the face of Big Ben. These hands are going around in the clockwise direction, right? And so there's going to be an angular momentum associated with their rotation. But if we're going to find the total, right, angular momentum, like all momenta, we can just add them together. So the total is going to be the angular momentum of the minute hand plus the angular momentum of the hour hand. And strictly, these are all vectors. So let's get the direction out of the way to begin with. We're just going to apply our right hand rule and figure out the direction of angular momentum of a clock face. What direction is omega for the hour and minute hands? Which way are they going? Clockwise. Ooh, I wonder where they came up with that, right? So we take our fingers, we wrap them around in the clockwise direction, and our thumb ends up pointing which way? Into the face of the clock, right? So we know the direction for all of this is going to be into the face of the clock, and I'm just gonna leave it there, right? Now, what if you had a weird situation where one hand was going clockwise, but the other one was going counterclockwise? It's broken, but you would subtract because the directions would be different, right? So you can add them as vectors. All right, so from here on out, I'm just going to kind of drop vector signs because I know they're both in the same direction and I know the total is into the face of the clock. Okay, so this means I need to find the angular momentum of the minute hand and I need to find the angular momentum of the hour hand. The minute hand, that's going to be the moment of inertia of the minute hand times the angular speed of the minute hand. And then moment of inertia of the hour hand, angular speed of the hour hand. All right. What do you want to tackle first? Moments of inertia or angular speeds? Moment of inertia? All right. What does it look like? Yeah, I'm thinking B. Right? It's a rod shape. I know the shape is a little bit more complicated, right? But that one definitely looks like a rod. This one just looks weird, but we'll treat it as a rod anyway, right? So this is about the closest shape we can get, right? And so we'll run with this one, right? 1/3 ml squared. When you're in doubt between like this one and this one, just go there. That's really all you need to do. Okay, so let's see here. 1/3. Whoops. So we're going to go with the moments of inertia are going to be 1/3 ml squared, and that's like for both of them, right? So the moment of inertia of the minute hand will be 1/3, and then the minute hand is 60 kilograms, okay, because it's the bigger one, and its length is 4.5 squared. And then I'm going to have moment of inertia of the hour hand, 1/3, and oh no, I did that wrong. 100 is bigger than 60. 60 times 2.7. There we go. Get all my numbers in the right place, and I might have a chance at getting it right. All right, I got, for the minute hand, I got 675. Did I screw up my units over here? Nope. Nope, no, I'm good. Never mind. My brain's just playing tricks on me. And then 1/3 times 60 times 2.7 is 146. Okay, so I got those out of the way. We're good to go. Okay, so now we've got to do the angular speed of both the minute hand and the hour hand. The problem didn't give me the angular speeds of the minute hand. All it gave me was masses and lengths. Am I stuck? No? Oh, we do have, for the minute hand, the angular speed of the minute hand is 1 revolution around the clock face every hour. Not minute, right? The minute hand, which tells us what minute it is, goes around once per hour, dividing the hour up into 60 minutes. Blame the Babylonians. Okay. So that's an angular speed. Do I need to convert it? Yeah, it's not in standard unit. What's the standard unit for angular speed? It's radians per second, isn't it? So I've got to take this thing and I've got to go, for every 1 hour, there are 3,600 seconds. And for every 1 revolution, there are 2 pi radians, right? And I'll get my angular speed of my minute hand to be 1.75 times 10 to the minus 3 radians per second. All right. Angular speed of the hour hand. All right, so the hour hand goes around once, 1 revolution every how many hours? 12. I know, it's hard to be young. Okay? How many? The face is divided up into 12 hours, not 24. Oh. Okay, boomer. I'm not a boomer. Right? But like, am I right? It's 12. I know it's hard. So it comes as a revelation to some, right? So again, same conversion factor, 2 pi over 30, no. It's not the same conversion factor. The revolutions was. 1 revolution, 2 pi radians, and forever. Oh, it was the same. 1 hour, there's 3,600 seconds. I just fooled myself. Okay, but it's still 2 pi over 3,600. But there's just a 12. 1.45 times 10 to the minus 4 radians per second. All right. Do we have all the pieces parts? Yeah. Looks like we know the moments of inertia, and we know our angular speeds, and we need to do some multiplying and some addition, which can be done. Let's see. So we'll do minute hand first. 675 times 1.75. That's supposed to be, there we go. 1.75 times 10 to the minus 3 plus 146 times 1.45 times 10 to the minus 4. Is this going to be a really big number or a really small number? Pretty small number. 1.2 kilogram meter squared per second, which, again, you have no reference for how much that is. But it is very small. And why is it very small? How fast is the clock face going? Very slowly, right? Okay. So it should come as no surprise that the angular momentum will be fairly slow. This is an example of being able to combine angular momentum and using the table for the moments of inertia of an object, that kind of thing. For other stuff that goes faster, angular momentum can be a lot bigger. So let's do a quiz. Smart me. All right. Okay. What was conservation of momentum way back when? Chapter 9, a whole, what was that, 2 weeks ago? Feels like forever, doesn't it? Spring break is coming, don't worry. So, back when we did conservation of regular momentum, the initial momentum had to be equal to the final momentum. Even if the initial momentum was 0, the final momentum had to be 0. It just might have been divided up against things going different directions or whatever. So I'm hoping it comes as no surprise that our conservation of angular momentum statement is really going to be the same thing. Whatever we start with has to be what we end with. The problem is, once again, what's an angular collision? Again, an angular collision is not two rolling bowling balls striking each other. That's a linear collision, okay? That's two center masses coming in a line and bouncing off of each other. Sure, there could be rolling motion associated with it, and you'd have to take into account all the energy, whatever, blah, blah, blah. But an angular collision isn't objects running into each other. There's one exception to that, and I'll describe it later. But I need to demonstrate what an angular collision looks like, okay? And what I brought here is, this is a seat, right? But it's on a rotating stand, okay? It's mostly frictionless. It'll spin for a while, okay? I call this my Michelle Kwan simulator, okay? Does anybody know who Michelle Kwan was? She was probably one of the greatest figure skaters of all time, okay? And she never won an Olympics, which just tells you how good the Olympics are. But in the sport of ice, in many sports, to be honest with you, but I'll single out ice skating, there are rotations. In fact, there's rotations that turn into straight line motion, and then there's straight line motion that turns into rotation. A friend of mine has a black belt in Aikido, which is a type of martial art. And he invited me to come to the dojo and watch them practice and get an idea for what Aikido was. I think he wanted me to get into Aikido, but what I got into was the conservation of angular momentum that was going on in that room. Because the sparring partners, one would rush at the other one, and the Aikido is a very defensive martial art. It's all about disarming your opponent and getting them flat on their face so they can't hurt you anymore rather than attacking them. And so you'd see this person just standing there, right? And somebody's coming at them, and then you'd blink and the attacker was on the ground, face down. And you're like, what just happened? And what they were doing, the martial art over the centuries has developed these techniques to take that straight line motion and turn it into a rotation that gets the attacker all discombobulated with their face into the floor, right? It's really, really quite impressive. In the case of figure skating, there's that move. Let's see, what do they have to do? There's all these elements that they're required to do, but there's the one where they're skating along the arena and they got like their hands out and, right? They're having to do that, right? Holding their leg up. And what do they do at the end of that move? Yeah, they pull, like they start to turn. They go from straight line and they start to turn, and then they pull their legs and their hands in. They stop moving in a straight line, and now all of a sudden they're spinning around, and it looks like they're going to auger a hole directly into the ice rink, right? So this stool, okay, is my Michel Kwan simulator because it's going to allow me to simulate that move without having to be physically fit in any way, shape, or form, except for the fact that I got to hold these up. Are these heavy? Oh, yeah. Yeah, okay. It's like 10 pounds. Okay, so I will struggle to hold these up because, physics muscles. But what I'm going to do, okay, and again, the stool rotates, right? So I can go around. What I'm going to do is I'm going to hold these out, okay, at arm's length, and I'm going to put myself into rotation. And then I'm going to pull them in. And I want you to watch what happens to my angular velocity before and after. You ready? Here we go. We'll push off the floor, pull them in, send them out. Go the other way before I get sick. So nice slow, and then I pull it in, and I speed up, right? Okay. Ooh. Why? What changed? Be more specific. Yeah, radius, distance. What changed? Not the mass, the distribution of mass or moment of inertia. Okay, wait, what? How did the moment of inertia change? The location of where the mass was changed, right? Okay, it went from mass being far out on either side to mass being pulled close to the center of rotation. So an angular collision in quotes here, right, is about changing the moment of inertia of a system. If the moment of inertia changes, then angular momentum must be conserved. If the moment of inertia decreases, then the angular speed has to increase and vice versa. This is not my chair. It is a chair, but it is not my chair. We'll put this one right here. Where'd my chair go? Okay. So let's get this written down. So it's not that things are hitting each other. It's that we're changing moments of inertia. So in a sense, right, I've got whatever my moment of inertia is to begin with, times whatever my initial angular speed is, equals whatever my moment of inertia is afterwards, times my final angular speed. You'll notice I kind of didn't, the vectors, I'll show you what's happening with the vectors here in a second. So let's do the example, right, of Mr. Balogh on the stool. Okay, so what have we got? We've got, okay, I've got to draw a picture. Okay, so before, here's Mr. Balogh on the stool. I tried, right? What we're going to do is we are going to model me sitting on this stool, right, we're going to model like the stool and like the core of my body, my legs, my chest, right? My head, everything. We're just going to call that like a cylinder, not a sphere. I mean, I'm not getting fat. I'm just expanding along with the rest of the universe. Trying to keep up. So we're going to go from, so we have this central like core, right? And then we've got arms, right? And then we've got these masses out at the ends, right? So a lot of things to keep track of. I'm going to just say, right? I'm just setting a number. Let's say we measured it in lab or something like that. But let's say that Mr. Balogh's core, right? The moment of inertia of the core is 3 kilogram meter squared. Again, it's just a measurement. It's just a given in the problem, right? What we have to determine is what to do about the arms and what to do about the point masses here at the end. Okay? So, and let's assume, let's go with the point masses at the end. We know that these both are, what did I write down? I don't know what I wrote down. What's 2, 1 mass? Oh, it must have been 3 kilograms. Yeah, each of these are 3 kilograms. Roughly 10 pounds. Okay, so we have what are we going to do about those? We need to, what I'm trying to do is find my total moment of inertia before I pull my hands in. And we're also going to say that these are out at 1 meter. Okay? So, how do we find the moment of inertia of these things? We go to the table, right? Table doesn't have any entries for a mass out at the end of a rod. So we just go to mr squared, right? The shape of these masses out of the ends of my hands didn't matter. Okay? What matters is that they were out there. Okay? So we're going to go ahead and use mr squared for each of these individual masses, right? Okay, what are we going to do about my arms? Look on the chart. Not given the mass this time though, right? I said the 3 kilogram mass. Well, it turns out I have physics arms, and they're massless. We're gonna ignore my arms, okay? They're wimpy anyway. So we'll just say that they're negligible, okay? Importantly, what my arms are doing though is they are pulling in the masses so that they come closer, right? So we're going to say that after they pull in, what did I say? It was like they were 30 centimeters away from the center of my chest. That's probably too much. It's probably more like 10 centimeters, but that's all right. It's the numbers I got in my thing, right? But the center will remain 3, still mr squares. It's just where those mr squareds are changes, right? So if I'm going to go and I'm going to find my initial angular momentum, the moment of inertia, I need to like add together everything in the system. So this is going to be the moment of inertia of the core, plus the moment of inertia of my masses. So that's 3 plus, and how many masses am I holding? 2 of them, times the mass times wherever they are initially, right? 3 plus 2 times 3 times 1 squared gets me 9, doesn't it? 9 kilograms meters squared. All right, and then I go find my final moment of inertia. So still the core plus twice the mass times whatever distance I'm at now. 3 plus 2 times 0.3, nope. 2 times 3 times 0.3 squared. Get my numbers in the right order. I cannot do this one in my head. What did I get? I got 3.54 kilogram meter squared. So what happened to the moment of inertia? Get bigger or smaller? Got smaller, right? Went down. Started at 9, went down to 3. So in my statement up here of conservation of angular momentum, I have I initial, omega initial, all divided by I final will get me my omega final. I just divided both sides by my final moment of inertia. So let's see here. My final angular speed will be my initial angular speed times like the ratio here, right? The I initial, where is that? 9 over 3.54. I didn't get that number. Let's say that I was going at 3/4 of a radian per second. Let's say omega initial was 0.75 radians per second. So that would be 0.75 times 9 over 3.54. I got 1.91 radians per second. So see there, my final angular speed ended up being higher. Why did my final angular speed change? The moment of inertia changed. That's the collision, right? It's not an impact. It's not even really an interaction. We've changed the moment of inertia somehow. And that is what is going to lead to our conservation of angular momentum. What is this? This is a transmission. Those of you that don't know anything about cars, don't panic. You're about to learn. So why do I have a picture of a transmission up here? The transmission's job is, in a gasoline-powered car, is to allow the car to change how it's using the engine's power in order to rotate the wheels. I'm guessing many of you drive a car that has an automatic transmission in it, and you'll feel the car shifting as you go, right? You hit the gas, and it kind of goes, right? Okay. Those of us that learned how to drive, anybody drive manual? Oh, good. It's still alive, right? Driving manual transmission cars, you know you can't start your car in 4th gear. Just doesn't work, okay? But those of us that have driven manual transmission cars also know that there aren't 2 pedals, there are 3. Human beings have 2 feet. So why is there a 3rd pedal? The clutch. What's the clutch's job? No. It detaches the engine from the parts of the car that make the wheels turn. Okay? Now, the clutch happens to be right next to the transmission. Okay? But a car that's running on gasoline, so some cars, some newer cars today, when you pull up to a stoplight, will actually shut their engines off, right? Just to conserve gas and not pollute. It's a good thing, right? But so ignoring auto start-stop capability in a car's engine, right? A regular car would have to keep the engine on even though we are at a stoplight. Now, in an automatic transmission car, this is handled for you, okay? But in a manual transmission car, you have to disengage the engine from the wheels. And the way you do that is with the clutch. You can either push the clutch pedal in, which completely disengages the engine from the drivetrain, okay? You can shift into neutral at that point. It's much easier to change gears when the engine isn't trying to tell the rest of the car what to do. And so you push in the clutch, you change your gear, you release the clutch. You burn out several clutches while you learn how to do that smoothly, right? But the clutch's job is to detach the engine, which is rotating. It's got pistons in it that are going up and down. Those pistons are connected to a drive shaft. That drive shaft is rotating. And it continues to rotate. As long as the engine is on, the drive shaft is rotating. The clutch will connect that drive shaft to the rest of the car or disconnect it from the rest of the car. If it does that smoothly, you never really notice. But if you do it too roughly, if your automatic transmission isn't tuned correctly, the car will jerk, okay, either in a gear shift or starting and stopping or something like that. So why am I talking about the transmission all of a sudden? You have a rotating drive shaft in the engine, and you have another piece that needs to rotate in order for the wheels to go. It's not rotating, but this one is. The clutch will bring those two pieces together to cause them to rotate together. The reason I'm talking about this is because that is the closest thing we have to an angular collision, right? Something that is rotating and then something else that isn't rotating, right? Coming into contact with each other, and then they begin rotating together. So you'd have the angular momentum of the drive shaft, you'd have 0, and then afterwards you'd have them coupled together, right? It's a little bit like our bullet catcher example, right? Where we just had the cannonball going at first, and then afterwards they were together. Only the rotational version of it. I gave you a homework problem where you've got, I think it's 2 discs that meet, they have a common axle, and I think part A is that the top one isn't spinning and you drop it down and find the new angular speed. And I think in part B, they're saying they're like spinning opposite directions and they come into contact with each other, okay? Yeah, don't be rolling backwards down a hill and try to throw the car into first gear. It's not happening. And for those of you that are interested, and even those of you who are not, my first car, my International Harvester Scout 2, I could idle up a 20-degree slope in first gear. Had a compound low first gear, which is another way of saying it was a tractor. Yeah. I heard that Scouts are back. The Scout company is back and they've made an EV Scout.
So is the VW bus.
I want one. What?
It's technically an improvement because it has better torque.
I'm not so sure. My first Scout had a lot of torque. I would usually, so it had 4 gears. I would usually start at a stoplight in 3rd gear. There was that much torque. Off of a cliff. Yeah. So yeah, yeah. No, electric motors do have more torque. Electric cars do not need transmissions. The motor itself is the transmission. The motors in an electric car only spin when the car is moving. When the car is stopped, the motors are not doing anything, right? Okay. If you've ever driven a golf cart, you've driven an EV. All right. All EVs are just glorified golf carts. All right. I want to now try to show you. I realize I forgot a key piece of safety equipment. So if I die, class dismissed. I want to show you how the direction of angular momentum is conserved. Phys demo only. Well, I'm doing a physics demo. Do not try this at home. This is a modified Dremel. Okay, we've put a different tip on it to do what I'm about to do. I've got my Michel Kwan simulator chair right here, right? Which is my freely spinning chair. And I have my bicycle wheel, only this wheel has its masses installed in the outer edge, okay? Now, physicists, we don't do sports very well, but we do understand that you don't want a whole bunch of mass on the outer edge of your tire. But in this case, we really do. Because what we want is a situation where the moment of inertia of this tire is as big as we can get it. So these are lead weights that are bolted into the outer edges of the tire to increase the moment of inertia of this tire so that I can show you what I'm about to show you. Right? Let me explain what's going to happen and then we'll do it. What I'm going to do is I'm going to spin this wheel up to a very high speed. Okay? And then I'm going to sit down on the chair with my feet on the floor, and I'm going to put the wheel into a situation where it's spinning somehow, and I'm going to need you guys to figure out the direction of the angular momentum. Both of my hands are going to be busy. I'm not going to be able to do it, okay? So if we're spinning this way, what direction is the angular momentum pointed? Down. And if it's spinning this way? Up. Okay. So I'm going to lift my feet off the floor, and then I am going to turn this over as fast as I can. Okay? What happened to the direction of angular momentum? It switched, right? But angular momentum must be conserved. Not just the number. I didn't change the magnitude of the angular momentum, but the direction has to be conserved as well. So what I want you to do is figure out the angular momentum of me after I flip it over. Before I flip it over, what's my angular momentum? 0. I'm not rotating, right? After I flip it over, use your right-hand rule to find the angular momentum of me. Okay, here we go. If I die, like I said, class dismissed. All right. Which way is it going? Okay, here we go. 3, 2, 1. Which way was I going? Down, right? It started down, and it ended up being down. Okay, with it still spinning, let's make it go faster. Let's see. Let's make it. This is hard work, and I'll show you why in a second. I mean, I know I am weak and all that, but this really is hard. All right, watch what happens if I hold the wheel and I try to change its angular momentum. It's like I have the force, right? Okay. Also watch this. Come on. See how I'm not holding it up. I mean, I'm giving it some support, but I'm definitely not giving it the right kind of support. If this were not moving and I tried to support it on the edge, what happens? It just falls, doesn't it? Right? But if I get it spinning, just hold it up, right? It's really important that you not get your fingers in the wheel, right? Do you see how it's not falling? But it is doing something called precessing. Do you see how it constantly is turning around? Okay? So what the heck is going on here? All right, I need a volunteer. Just real quick. Somebody that wants to come play. Abraham, come up here. Okay, I want you to grab the center here. Okay, yeah, both hands. Okay, you got it?
Yeah.
Got the weight of it? Now try to move it. Just try to put, what's it doing to you?
It's like pushing against me.
Pushing against you? Is it fighting you as you go? Okay, how strongly is it like fighting you? Pretty strong? Yeah. Try to move it quickly. How strong is it fighting now? A little bit stronger. Okay. So don't take my, give a hand to Abraham. Okay. let me show you. All right. I'm going to try and throw this a little bit. I'm going to hold on to it. But watch what this is not an exaggeration. It really fights. The faster you try to change this angular momentum, the harder it fights, because angular momentum must be conserved. Direction as well as magnitude. What direction is the angular momentum of this? What direction is the angular momentum of this pointing? Towards you, right? And so if I try to make it, if I try to make it go up, then it's going to try to turn me down, right? But I'm planted on the floor, so I don't change. But when I was on the seat, I started spinning, right? Angular momentum must, put this down. Oh, not only is it heavy, it fights you the whole time. So if you have a satellite in space and you want to stabilize it to make sure it only points in one direction, what do? Make it spin, okay? I've told you that I'm a bad person already, so this will come as no surprise. Big box stores. If you work in one, I'm sorry. Notoriously, the people that work in big box stores are trained to be friendly. I'm not sure they're trained to know anything about the products that they sell. So I, one day, walked into a big box store. I was looking for a leaf blower. And I wanted a leaf blower that had its fan mounted horizontally, not vertically. Why is that? Leaf blowers that have the fans mounted this way, if the fan is spinning around, do you see how you're constantly having to change the angular momentum? You're fighting the change in angular momentum. Whereas if it's installed this way, okay, you're not fighting the angular momentum because it just points up or down no matter what. So guess what I did? No. I walked in, and a poor young man came up to me and was like, "Do you need some help, sir?" And I said, "Well, sure." And he said, "What can I help you with?" I was like, I would like a leaf blower that maintains its angular momentum vector. It is. It's very mean. It's very mean. And he just looked at me. He's like, and then the face sort of changed from confusion to, is this what I call security? I think that was in my training somewhere. When, you know how in big box stores they have the things stacked up in big rafters, right? And sometimes you can see through and other times you can't, but you can always hear the marital arguments that are going on in the other aisle. So we were standing there in one of these aisles, and from the other aisle, I heard someone shout, "He wants one with the fan mounted horizontally." These are my people. I was like, who said that? Who is that? And around the corner came one of my 4A students that had the lecture like 2 or 3 weeks earlier. Big old smile on his face. Do I get extra credit, Mr. Balogh? I was like, no, but you get a high five. Like, this is awesome. This is great. Angular momentum must be conserved. I will see you next Tuesday, right? Unless you come to grass, which you should, because homework is hard.